We've got Dawson with us. I wonder who else we've got. Let's look and see here. Oh, we've got a good crowd. We've got Alex, Nathan, Braxton, Dawson, Mohammed, Julian, Bryce, Reagan, and Nicholas. Got a good class. Okay. The topic today is the diesel cycle. Before we begin, do you have any? And we got Braxton too. Got a good crowd there. Bryce, Brian, Alex. Do you have any questions for me?
Yes, I do.
Go ahead. Go ahead, Reagan.
Yeah, I want to ask about the grade. Is nothing updating? Like, are you going to updating our grade anytime soon, or just
on Blackboard, you mean?
Yeah, on Blackboard, yes.
I think I put all of your exam 3 grades on Blackboard. Can you find exam 3,
yes,
Reagan?
You did. I'm talking about that extra point from question 1.
Oh, yeah. You know what? You got 5 points.
Mm-hmm.
I have it marked in my book here, Reagan. But you're absolutely right. I didn't put it on Blackboard.
Okay.
But I will.
All right.
But
thank you.
Yeah, thank you for reminding me. But you guys have to know something. I go by my record. The Blackboard is just for the bosses, the administration. In case I die and they have to give you guys a grade, they've got all that stuff on Blackboard. And so my boss would figure out your grade. See, I'll be dead, okay? And my boss will figure out your stuff. I guess he could get this stuff here that I have from my wife, but hopefully I'll make it through the semester. What do you think?
Of course, yes, you make it.
Good. Yeah, but don't you worry. I'm not gonna shortchange you at all. Now, I don't know if everybody got the word. That was on exam 3. Reagan, what was that? Was that problem 1?
Yes, problem 1.
Yeah. Look on content, everybody. And if you got that problem 1 right, it's explained on content, you can get 5 more points. If you got it wrong, well, too bad. Now, if you got it wrong and I marked you right, I'm not taking any points away from anybody. That's not very nice. If I make a mistake, you shouldn't have to pay for it. But thank you for speaking up. Anybody else before we tackle this?
Yes. Mr. Griffin.
Yes.
I have a question. So on the Blackboard, I think the homework problem number is like a little bit up and down. So we're missing the homework number 24. But I think on the Blackboard, instead of homework 24, they put 25.
Yeah. Well, here's what I thought. There was a confusion about this. Homework number 24, I thought it was problem 917. And homework 25, I thought was
106E.
yes, 9106E. And problem 26, and I don't know what happened. I'm just not happy with doing this online stuff. I was a lot happier before we had to do stuff online. But that one was 965. I'm coping the best way I know how here.
You just skip the homework number 24. That's it. But we still submit you the same homework, 917 and 106, but on a different homework number.
Okay, well, if you feel like you've been shortchanged, email me and we'll fix it. Okay. All right. Anything else? Okay, well, we're going to do a Rankine cycle, but now which one? I wanted to do a Rankine cycle. This is, I'll tell you what it is. It's 10. Problem 10, chapter 10, 122E. That's what we're going to try to do. Now, let me see if I can find it here. Okay, I'm looking for 10, 122E. It's a Rankine cycle. It's in English, senor. It's in English. Diesel engine, okay, with a CR, that stands for compression ratio. What that is, a compression ratio what that is, it's V1 divided by V2, and they said it's 20. Now remember, the Rankine cycle has on a PV diagram, you want to start off here with your compression. This is your compression stroke. And use the numbers that they use in the book. This is how they do it. And if you change the numbers, you'll get me all confused. So just do it the way the book does it. There's your compression stroke, and this is the burn. It's an isobaric burn to state 3. There's state 1. And then what you have is your power stroke. You get a little bit of power out of your burn, because that moves your piston some, and you get some power out of the burn there. See, on a diesel engine, you got a lot of compression. I mean, this is 20 to 1. V1 over V2 is 20 to 1. The compression really goes up, so much so that it heats it up and makes it hot. And that explodes the diesel. And that's what makes the loud banging sound. When a diesel goes by, they're loud because it's exploding that diesel fuel. And you have an isobar from 2 to 3, and then you have your power stroke. And then they model the exhaust intake as an isochore. This is the exhaust. This is your power stroke. This is your burn. This is your compression. See, these two are adiabats. They're adiabats. These two are adiabats. This is an isobar. It's an isobar. And this here is an isochord. So there's your diesel cycle. And we're going to read this. It's 10122E. And it says the inlet is 520 Rankine. Well, let's get some red here. If you drew the isotherms, that's 520 Rankine. We're in English now. And do you notice that the adiabat is steeper than the isotherm? Adiabats are steeper than isotherms. Write that down. And see, this here is your hottest temperature. And do they tell you what that is? Yeah, 3,200. This is 3,200 Rankine. That's your hottest temperature. Let me keep reading here now. Maximum pressure, 920. They said the maximum pressure here is 920 PSI. So we've got our isobar there. The pressure will be the same at 2 and 3. Well, that's about it, guys. We're ready to do our problem now. And what we're going to do, if you have any problem with these, email me. We'll figure it out. I need the space here. We're going to make our table now. Here we go. We're going to have P, V, T, delta U, Q, and W. And we'll have process 1 to 2, 2 to 3, 3 to 4, and 4 back to 1. It's a cycle. And let's put the units in there because units are important. These are PSI. These are cubic feet per pound mass. We'll do these in Rankine. This will be BTUs per pound mass, BTUs per pound mass, BTUs per pound mass. And you all remember what a BTU is. A BTU is the amount of energy needed to heat 1 pound mass of water 1 degree Fahrenheit, or Rankine, same difference. All right, well, some of this stuff is known. If you'll read what they said this is 920. The pressure at 2 is 9. See, these are all the initial values. Put a little I on all that if you want. The initial value of the pressure going from 1 to 2, we don't know. Don't know what that is. They don't give it to you, do they? Let me read it again here. And we're doing 10, 122E. No, they don't tell you. Well, they do tell you what the initial pressure going from 2 to 3 is. Going from 2 to 3, the initial pressure is 920. Okay, 920 PSI. Hey, you know what? The initial pressure going from 3 to 4 is also 920. There's your isobar. So we've got that. Now, what else do we know? Hey, wait a minute. It's state going from 3 to 4, the initial temperature is 3200. So that goes right here, 3200. Rankine. Hey, looky here. P3V3 is equal to RT3. We can figure out V3. Okay, well, let's put in our numbers and do it. So this is 920 pounds force per square inch. That's what a PSI is. And this V3 will be in cubic feet per pound mass. Now the R is 5334 foot-pounds force, pound mass Rankine. And the temperature at state 3 is 3200 Rankine. So look here, we know everything. We can find V3. But there's a dirty little catch. If you forget this 144, you won't get the right answer. You got to go 144 square inches is a square foot. Then you'll get the right answer. All right, I'm going to shut up, and I want you to find V3 for me. And then I'll call on somebody. Go for it. Now let me go to my friend Alex. Alex, unmute and say hi, please.
Hello.
Hey, Alex, do you have this specific volume at state 3 for us?
I got 1.28841.
That's what I got. I got 1.288. That's probably enough accuracy there, Alex. Now, I put it in the wrong place, though. I goofed up. It goes here. I goofed up here. But hey, I caught it. You don't get a thank you point when I catch it. You got to catch me. There you go. Now we did good. We got that. Now what? Hey, what about these adiabats? I need to put some zeros in here. Let's pick on my friend Alex again. Alex, you did good on this little V here. Where do I put my zeros for my heat transfers, Alex?
Would it be at 1?
Yeah, 1 to 2. See, going from 1 to 2, look here, Alex, 1 to 2 is an adiabat. There's no heat transfer. What's the other one, Alex?
3. 3 to 4.
Yeah, it's going from 3 to 4. Good going. Now, one of these work per masses is 0. Let's pick on somebody else. Braxton, unmute and say hi.
Hello.
Hey, Braxton, one of these little work per mass deals here is 0. Which one is it?
I'm gonna guess 4-1.
I like it. I forgot to put my 4 in there. There's state 4, and there's state 1, and there's no work done. Braxton, how come there's no work going on that?
Because it's exhausting, and on a PV diagram, I feel like you need to go left or right, and the work under it is.
That's right. You got it.
Yeah.
Exactly. You got to go left or right to get any work done, and it's just going straight down. It's called an isochore. The piston started and ended at the same spot, and we're treating it as an isochore, and so you get 0 work done. In reality, the engine really turns over physically 360 degrees because the piston comes up and you have your exhaust, and the exhaust goes out, blows some smoke out there, and it stinks. And then the piston goes down and it sucks in some diesel fuel. But we're treating it as if it's an isochore. Thermodynamically, it's an isochore. Physically, it's not. Okay, well, we're coming right along. Now, they said V1 over V2 is 20. Is that going to help us any? Let me write that down. That's called the compression ratio. Nah, that's not going to, look, that's not going to help us any because we don't know V1 or V2. Never mind that, it was just a thought. But let's see. At state 3, we've got an adiabat to state 4. So we can use an equation that we know and love. I need to make some room here. We're doing an ideal diesel cycle. We're assuming each process is reversible. And this is an adiabat or reversible adiabat. And reversible adiabats have a special name. And I'm going to call on one of my excellent students here. We've had this before, but you might have forgotten. Brian, unmute Brian and say hello, please.
Hello.
Hey, Brian, there's a special name for reversible adiabats. What is it?
It's something like ison.
You got it. By Jove, he's got it. It's isentrope.
Okay.
And what it means is the delta S is 0. Delta S is 0. Well, so what? There's no S's on here. But wait a minute. We've got an equation for isentropes. If you have an ideal gas, and did you know we're dealing with air basically? It's got a little diesel fuel in it, but basically it's air, which is an ideal gas. So T4 over T3 is equal to P4 over P3 to the K minus 1 over K, which is equal to V3 over V4. If you don't have this equation written down someplace, write it down. It's a nice equation, but be careful. It only works for an isentropic ideal gas, which we have. We've got an ideal gas. It's air. At these temperatures, air behaves nicely. Now, do we know T3? We do. Do we know T4? No, we don't. Do we know P3? Yeah, hey, we know P3. Do we know P4? We don't. Do we know V3? Hey, we know V3 and we know K, right? We can look it up. Do we know V4? We don't. Too bad. It was a nice idea, but I don't think we have enough information to solve that equation. We're just up a creek. You guys got any ideas? I'm going to take a drink of water here. We're stuck right now, aren't we? We need to fill in those boxes.
Is 1 and 2 at the same temperature?
No, 1 is at 520 and 2 will be at a different temperature. Can you tell? It's going to be somewhere in between these two red lines.
Yeah.
Nope. But thanks for asking. It was a nice thought. But no, that didn't seem to work. Well, we just seem to have a huge problem here. Now, just a minute. Now, wait a minute. Auga. We do know what T1 is, don't we? I didn't write it in. Let's write it in. Let's write in everything we got here. Isn't T1 520 Rankine? See, we don't give up easy around here. We think T1 is 520 Rankine, but we don't know T2. Hey, I got this brilliant idea. See, when I think of an idea, it's brilliant. Aren't you the same way? Look here. Let's try this same little trick here, but let's go from 1 to 2. T2 over T1 equals P2 over P1, K minus 1 over K equals V1 over V2 to the K minus 1. If you don't have that written down someplace, write it down. We derived that equation. One day, go back and watch YouTube. Hey, is my TI person doing a good job on putting that stuff on YouTube? Can you guys find the lectures on YouTube? Can you? Somebody say, uh-huh.
Uh-huh.
Good. Well, somewhere in one of those lectures recently, I derived that. And look at here, guys. We know what this is. It's 20. And we know what this is. Look here. This is 20, 1.4 minus 1. And one of my excellent students asked about T2. And we don't know what it is, but we know what T1 is. It's the 520. So put it in. Here we go. 520. Rankine. Okay, now look, we got an equation. There's only one unknown. We're going to find T2. Here it comes. I'm going to shut up. I'll give you a minute and a half if you need it. Find T2. Go for it. Well, I think I've got T2. Let me go to one of my excellent students here. Bryce, unmute and say hello, please, Bryce.
Hello, please, Bryce.
Okay. Hey, Bryce, did you get T2 from this equation yet?
I believe I did. I got
What'd you get?
1723.516 Rankine.
That's exactly what I got. I got 17. Oh, come on. I'm in a little trouble here. Here we go. 17, 23. Did you say 23? 1723?
Yes, sir.
Bryce? Yeah, that's what I got. I got 1723.5 Rankine. And I want to know if anybody else got that. Say if you did. There's one. I heard an Okay, now what we're going to do is we're going to find little v2. Okay, little v2. Now I could write it out for you, but you don't need me to write it out. You know how to, if you know the pressure and the temperature, you can find the specific volume. I'm going to do it. You do it. Find V2, go for it. You got a minute and a half if you need it. Well, I got an answer. For V2. I got point. Come on now, 0.6939. If you got 0.6939, say If you didn't get 0.6939, say Well, I didn't hear any uh-uhs.
I mean, I got 6940. It's still close, so it's okay.
Oh, you rounded off.
Yeah.
I think you're probably all right. I wouldn't worry about that. Anybody need help with that, or are you okay? Well, I bet you're okay. I have confidence in you. All right. Now, guys, I need the room here. Let me make some room. They said, this is going to be neat. They said that V1 over V2 is 20. They call that the compression ratio. Well, look at here. If you know V2 and you know 20, well, we can figure V1. Okay, go ahead. Find V1 for me. Go for it. Did you get 0.03469? 69. You can make it. let's just round it off to 0.347. That'd be good enough for me. If you got that, say uh-huh.
Didn't get that.
Was that a yes?
No, I didn't get that number.
I didn't.
Oh.
I did not.
Well, I could be wrong. Guys, I could be wrong. Here, let me, to get V.
I get 13.881.
Oh, I'm wrong. And you guys are right. I am wrong. And you guys spoke up. I'm proud of you. Okay, let me do it again. How about 13? How about 13? I did it backwards, guys. I goofed up. How about 13.88?
Yeah.
Are you happier now?
Yeah, that's what we
Yeah,
got.
good. I appreciate you guys. I think I did it upside down. Okay, now we're going to find the pressure. Now let me make some room here. We're doing great. We're going to find the pressure now. At state 2. Oh, wait, no, wait a minute. No, wait. No, this is the pressure. I'm getting confused. Oh, no, we're trying to find the pressure at state 1. That's way the heck over here someplace. The pressure at state 1. Well, we can get it. You know how to do it. P1V1 is equal to RT1. And see, we know V1. We know R for air. We know T1. I'll shut up. I'll let you get it. Don't forget the 144, though. I got a value for P1. But I'm going to call on somebody. Let me call on my friend. I'm going to call on my friend Nicholas Sabrata. Nicholas Sabrata, unmute and say hello, please, Nicholas.
Hello.
Nicholas, did you get, what are we doing? Did you get P1?
I am a little confused here. Do I
Okay.
multiply or do I divide by the 144?
Here, let me write it out for you. You go 144 inches squared per foot squared times V1. Now V1, see, that's going to be foot squared or foot cubed per pound mass. This is 5334 foot pound force pound mass Rankine. And the temperature is 520 Rankine. See, the Rankines cancel, and you'll have foot pounds per pound mass on the right. And over here, you'll have
We're missing the pressure.
Oh yeah, I'm missing the pressure. Here's the pressure, and see what that is pound force per square inch. The inches cancel, and you'll have foot pounds because there'll be a foot left up here times the pound. You'll have foot pounds per pound mass on the left, foot pounds per pound mass on the right. So to answer Nicholas's question, Nicholas, to find this V, you're going to have to divide.
Okay. I found P1.
What'd you get?
13.88.
That's what I got. Good going. We got the P1. It's 13.88 PSI. All right. Now what? Well, we seem to be missing a few things.
Professor?
Yes.
You put the P1 and P4.
There's another thank you point. Now, who was it that just helped me?
This is Nicholas.
Nicholas Sabrata? Nicholas
Yes, sir.
Sabrata?
Yeah.
Good going, Nicholas. You are now in the elite group of people with thank you points. It's like a club. Good going. Now, wait a minute. You know what's really weird? But I think it's correct. I think these are both 13.88. I think we did them correct. But see, this is PSI, and this is cubic feet per pound mass. But those answers are correct. It's just one of those strange coincidences in life. Hey, we're doing great, but hey, we don't have these yet. You guys have any brilliant ideas on how we're going to get those?
The I4, so you can, at 4-1, you can put 13.88.
Oh, I love it. I love now who was that?
That was Bryce.
Bryce, I'm going to give you kind of a dash thank you point. I didn't make a mistake, but Bryce has helped us that 4 and 1 have the same specific volume. So it should be 13.88, right, Bryce?
Yes.
Yes, the specific volume should be the same. Hey, that helps a bunch. Hey, Bryce, as long as you're coming up with these great ideas, any ideas for these?
Let me think. So the, oh, no.
Hey, Bryce, I got an idea.
So.
Check this out. Now, we had this up here earlier, but we didn't have enough info. But maybe we do now. Let's look and see. Let's look and see if we got enough info to do it now. Now we've got T3. Do we have P3? Do we have P4? No, we don't. Do we have T4? No, we don't. Do we have V3 and V4? Ooh, looky here. Looky here. We have V3 and we have V4. I think we can do this. Let's put in our numbers. T4 over, what's T3? That's 3,200. Does that show up? Pretty good. Yeah. Equals V3, which is 1.2884. V4 is 13.88. 1.4 minus 1. Okay, solve for T4. I'll be quiet. Solve for T4. Okay, well, I've got what I think is T4. I wonder, Julian, let me pick on Julian. Julian, unmute and say hello, please, Julian.
Hello.
Hey, Julian, do you have this T4 for us?
I'm getting 1236.56.
That's what I'm getting. I'm getting 12. Oh, come on now. 12, 36. Hey, we'll just round it off to 6. Hey, look at here. We have V and T. We can get the P now. Let's do that. Let me make some room here. P4, V4 equals RT4. And see, we know T4, we know R, and we know V4. We should be able to get P4. All right, I'll shut up. I want to see if you can do it. Go for it. Don't forget the 144. Well, I got an answer. I got 33.0 PSI. If you got that, say uh-huh.
Uh-huh.
Well, there's two of us. That's good. Well, let me put in my isotherms. I need to finish drawing my PV diagram. We now know that the temperature at 2 is 1723. So 1723. 1723.5 Rankine is the temperature at 2. Now the temperature at 4 is 1236. 1236.6 Rankine. Now we have all of our temperatures in there. We're doing great. Now let's get these little delta U things, our change in specific internal energy. Now, how do you do that? Well, there's a nice equation that goes like this that we all know and love. It goes, we'll do that. The only thing is, what's C sub P in English, senor? I think it's 0.24, but maybe we should look it up. Go to the back and look up C sub P for air in English, senor. Well, I'm trying to find it here. C sub P. We're doing air. By Jove, that's right. From memory, I got that right. How about that? My memory is still okay. I don't need to go to a rest home yet. Now, what's the what's the change in temperature? If you're going from 1 to 2, then what is the difference in temperature? Got hotter. Okay, well, we can do that. From one to 2, well, you're going to have to subtract these. You know what you're going to have to do? You're going to have to go 1723.5 minus 520 Rankine. Do I hear rain going on outside? Is it raining at your house? Is that my imagination? I think I hear rain. Okay, well, let's do it. Here goes. 0.24 times 1723.5 minus 520. Well, I got an answer for delta U. I'm getting 288.8 BTUs per pound mass. How about you? And see, now we can get the work done going from 1 to 2. Now, how do you do that? Well, you could use the first law. See, we're treating it as a control mass. It's like a piston cylinder. We're really lying to you because there is some valves and stuff comes in and out, but we're treating it as a control mass where you're just transferring heat in and out. But the first law says for control mass, look here, from 1 to 2, if you're going to go from 1 to 2, we have the delta U. Isn't that nice? And we have the Q. Hey, we should be able to get the work done. I'm getting a negative 288.8. How come it's negative? How come it's negative going from 1 to 2? Let's see if somebody can tell me that. How about my friend Nathan? Nathan, unmute and tell the class why the work per mass is negative going from 1 to 2.
Well, the change in volume is negative. I guess you could look at it that way, but it's leaving.
That's good enough. That's good enough. Now the answer I wanted, you know how teachers want to hear the answer they want? Yeah. The answer I wanted was it's compression, and compression work is negative.
Can I try that again? It's compression.
Yeah. By Jove, he's got it. He's catching on. He's catching on. Now see, expansion work is positive and compression work is negative. Have I ever told you that before?
Yes.
Oh yeah, I've told you. Well, let me tell you again. Compression work is negative. Expansion work is positive. Maybe I'll need to tell you another time or two. We'll get it eventually. Okay, next. What are we going to do next? Well, I don't know. Well, let's get this one. This here, we got to go back to that same equation we just used. Delta U from 2 to 3 is equal to C sub P. So that's that 0.2240 times delta T from 2 to 3. Go ahead, get that. I'm going to do it, and we'll put that in. Here goes. Well, I got an answer. I'm getting 354.4. How about you? I got a different number when I did this before. Let me do it again. Maybe I did something wrong. $354. No, that's what I'm getting. 354. Anybody getting that?
Yes, I'm getting
Yes.
the same.
Yeah,
That's
good.
what I got.
We're doing great. Hey, now, oh, wait a minute. Now, we don't know either one of these. There's two ways to get those. Let's do it both ways, shall we? We'll do it both ways. Now, one way is to get this Q. This is an isobar. And the Q for an isobar is equal to your delta H. Have I told you that? Yeah, I've told you that. And delta H is equal to C sub P delta T. Right? Now, wait a minute. Oh, God. Did I do the wrong one here? Yeah, this is wrong. Let me get this right, guys. I gave you some wrong stuff. Delta U is equal to C sub V delta T. What I just did was delta H. That's C sub P delta T. Now we got the right answer for delta H, and that's equal to the Q. We just did the Q, but the delta U, that's C sub V delta T. Now C sub V is 0.171 if you look it up in the back. And the delta T is the same as it was before. It's 1723 minus 520, right? We're going from 1 to 2, aren't we? Yeah, we're going from 1 to 2. And so do that for me and we'll get the delta U. I did it wrong, but I found it there. I think we'll be okay. We can check it. I'm getting 205.8. 205.8. Anybody getting that? I hope so.
Uh-huh.
Was that an uh-huh?
Uh-huh.
Oh, good. Now here I'm going to check it now. Now here's how we can check it to make sure we did this right. Little w from 1 to 2. That's just the area underneath this graph. You guys know that. Here, let me color it. I'll color that area green. You know that the work done is the area under your graph.
Would that not
know
be
that.
is that not the area from 2 to 3?
Oh, no, wait a minute. Yeah, that would be the area from 2 to 3. I'm sorry, what are you telling me?
You just wrote work from 1 to 2, but it's fine.
Oh, that's, I want 2 to 3. Now, who was it that just spoke up?
Bryce.
Bryce, you just got yourself a thank you point. Is that your second one today?
I got a dashed line the first time, so.
Oh yeah, well this one here is for real, man. I made a mistake. See, when I make a mistake, you get a nice big thick real one. You just helped us on that other thing. Now we're going to get the area of this, and that's the work done. Okay, let's do it. They teach you in calculus that the area under your graph or is equal to integral, right? Well, what's that area equal to? Well, it's a base times the height. It's just a rectangle. Now the height is 920 psi, pounds force per square inch. And the width of the rectangle, well, that's just V2 minus V1. You know what that is? That's a point. No, it's V3. We're doing 2 to 3. It's 1.2884 minus 0.6939. Isn't that how you do rectangles? Base times height? I do that, and we'll get our work from 2 to 3. Here it goes. Now, wait a minute, though. You know what these are? These are cubic feet per pound mass. You're going to have to multiply this by 144 to get rid of the cubic feet. Do that. Multiply by 144, and we'll have our, right? I ran out of room there is my problem. Those are cubic feet per pound mass, aren't they? Now I'm getting mixed up, guys. Just a minute here. No, I think we're okay. I think we're going to get foot pounds. I think we're going to get foot pounds per pound mass. But if you want BTUs per pound mass, you're going to have to divide. I don't have enough room is my problem. You're going to have to divide this by 778 to get the BTUs. Okay, that times this here, multiply 144 divided by 778. Let's see what happens. Here, let me write it here so you can see it better. I did all of this, and what I'm getting is 546.94 pound force square inches times cubic feet per pound mass. And see, you have to multiply it by 144 square inches per square foot and divide it by a BTU is 778.67 foot-pounds force. There, I barely have enough room to write it. Okay, so here we go. I got an answer. I got my work to be 101.1 BTUs per pound mass. Anybody getting that?
Yes, sir.
Now here's the proof. Was that a yes?
Yes, yes.
Good. And here's the proof of the pudding. If you subtract these, do you get 205.8? According to the first law, you should. Delta U should equal Q minus W. Well, let me try it. 354.4 minus 101.1. Must have done something wrong. 354.4 minus 101.1. I don't get that. Something bad happened.
I think your delta U is wrong.
Let me do the delta U again. Now, who am I talking to?
This is Braxton.
Okay, Braxton. My delta U should be, I think I have the right numbers here.
I think you're using from 1 to 2 instead of 2 to 3.
We're trying to do 2 to 3, aren't we, Braxton?
Uh-huh.
Braxton, I appreciate you so much. Something was bad, I know that. And so this should be, let's get it right. This should be 3,200 minus the 1723.5. Okay? All right, here goes. That delta U is wrong, guys. I think we did these right, though. But my delta U is wrong. Okay, here goes. 0.171 times 3,200 minus 1723.5. There's a point right there. 1723.5. 254.5. Now, if you subtract 354.4, well, I got 101 point something. It's a little off. It's a little off, but I think it's. I think we're okay. You take this minus that, 354.4 minus 101.1, 253. I'm off just a tad here. I wonder what I did when I did this. No, those are the right numbers. They're a little bit off, but I can't help it. They're not much off. I think it's a round off problem. Okay, well, let's finish this off. Delta U here should be 0.171 times this difference here. Let me do that. 1236.6 minus 3,200 times 0.171. Going from 3 to 4, I'm getting a negative 335.7. And now the work, I'm so disgusted with these things. Maybe this red one works better. Let's try it. 335.7. That's negative. This work comes out plus 335.7. Going from 3 to 4, it's positive work. You're expanding. And then here you have to subtract, going from 4 to 1, you have to take the 520 and subtract the 1236.6. I am getting negative 716.6. Wonder if I did that right. That looks right. And so what is the Q going from 4 to 1? Well, it should be a negative 7. It's exhaust. That's what's happening. You're heating up Oklahoma. Okay, now let's add these up. When you add these up, they're supposed to be the same. Let's see if you do. I'm adding all these up now. Well, I got 148 when I added all that stuff up. Now I'm going to add this stuff up and see what happens. Something really bad happened.
I didn't get the delta U as minus 716.6. I'm getting minus 122.53.
Okay.
That's what I had too.
Let me do, that's Mohammed and another wonderful student helping me out. This is wrong. Let me do it again. Now to get the delta U, you go 0.171 and you multiply the difference between 4 and 1, right? Which is 1236.6 minus 520. Oh, I think I see my problem. I forgot to multiply by the 0.171. It's a negative 122.5. Is that better, Mohammed?
Yes, sir.
Good. And so this would be going from 4 to 1 would be a negative 122.5. Now we're going to add these and see what we get. Okay, 354.4. Well, that still doesn't work out right.
I got a different U for 1 to 2. We originally did it with the CP value of 0.24, and I did it with 0.171 and got 205.8.
You know what? It is 205. Well, I got 205.8 when I did this last night. What would you get?
That. I got 205.8.
Thank you. Who is that I'm talking to?
Alex.
Alex, you're on the board. I'm proud of you. You did good. And so this should be a negative 205.8, shouldn't it? Now let's add this stuff up and see what happens. Here goes. This is the proof of the pudding. I'm getting 129.9. Now I'm going to add that stuff up. No, it's still not working, guys. It's still not working.
When I added up at work, I got 231.18.
Well, this here is 231.9. My problem is I can't add. Let me try again. And who was that just talked to me?
That was Alex again.
Well, this time I'm getting 129.9. Is that what you got, Alex?
I keep getting a 231.18.
Okay, well, let me try one more time.
It's just 335.75 plus the 101. Yeah, I keep getting 231.
You have 335.7?
Yeah.
Oh, I think I forgot it. I think I forgot to add the 101 point. I just added the red stuff. Oh, gee. Let me try again. Hey, I'm getting 231 this time. This is starting to look a little better. I'm still off a tad, but we're okay. Let me show you one last thing. We have 2 minutes. And that is the efficiency. I just need some room to do that. These are supposed to be the same here, guys. I erased that, doggone it. But they're pretty close to 231 there. The efficiency is the net work divided by this heat transfer that you gotta buy some diesel fuel. It costs money, you know. They don't give it away. And that diesel fuel is this 354. And the network, we differed, some of us, because I kept goofing up a little bit, but it's awfully close to that. And so the efficiency is 65%. Now, that does not mean you're going to really get a 65% diesel engine, because this one, we're assuming it just runs reversibly, no friction. Well, I showed you how to do it. I also showed you how to add and subtract incorrectly. I hope you can forgive me, but we can, if we're determined enough and stubborn enough, we can get the right answers. And I think we did pretty good finally. Unfortunately, our time together is over. And we do not meet Thursday. It's Thanksgiving. So you guys have a happy Thanksgiving. Be careful. And I will see you next Tuesday at what, 11 o'clock? I think so. So we're going to say bye-bye for now. Bye-bye, students.
Bye, Mr. Griffin.
Yeah. Bye. Have a good Thanksgiving. See you Tuesday.